Logic gates. Logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on a certain logic. Based on this, logic gates are named as AND gate, OR gate, NOT gate, etc. AND gate IC7408. The AND gate performs a logical multiplication commonly known as AND function. The output is high when both the inputs are high. The output is low level when any one of the inputs is low. A circuit which performs an AND operation is shown in figure. It has n input, n greater than equal to 2 and 1 output. Formula for AND gate. Logic diagram for AND gate. A and B are the input, Y is the output. Truth table. Here, if we put 0, 0, you will get the output 0. 0, 1, you will get the output 0. 1, 0, output 0. 1, 1, output 1.
So here is AND gate. In this AND gate, we need to switch as an input. So I took two switch as an input, and we should give an AND gate. And to get an output, I took one bulb. So I connected switch to the AND gate and end of the AND gate to output bulb. So after when I give 0, 0, I will get as 0. If I give 0, 1, I will get the output 0. If I put 0, 1, 0, I will get 0. If I get 1, 1, I will get an output 1.
OR gate IC7432. The OR gate performs a logical addition commonly known as OR function. The output is high when any one of the inputs is high. The output is low level when both the inputs are low. Formula for OR gate. Logic diagram for OR gate. A and B are the input, Y is the output. Input 0, 0 will get the output 0. Input 0, 1, output 1. Input 1, 0, output 1. Input 1, 1, output 1.
To give the input, I'm going to take two toggle switch to give two input. And we are going to do OR gate, so I took one OR gate. To get the output, I took a light bulb. So connect the wires. Okay. When both the inputs are 0, the output will be 0. When any one input is 1, the output will be 1. When both the inputs are 1, the output again will be 1.
Gate IC7404. The NOT gate is called an inverter. The output is high when the input is low. The output is low when the input is high. Formula for NOT gate. Logic diagram for NOT gate. Here NOT gate have only one input and one output. Truth table for NOT gate. Input 0, output we will get 1. If we give input 1, we will get the output 0.
NOT gate. When the input is 0, the output will be 1. When the input is 1, the output will be 0.
Gate IC7400. The NAND gate is a contraction of AND NOT. The output is high when both inputs are low and any one of the inputs is low. The output is low level when both inputs are high. Formula for NAND gate. Logic diagram for NAND gate. Truth table for NAND gate. Input 0, 0 will get the output 1. Input 0, 1, output 1. Input 1, 0, output 1. Input 1, 1, output 0.
NAND gate. When both the inputs are 0, the output will be 1.
When any one input is 1, the output still be 1. When two inputs are 1, the output will be 0.
NOT gate IC7402. The NOT gate is a contraction of OR NOT. The output is high when both inputs are low. The output is low when one or both inputs are high. Formula for NOT gate. Logic diagram of NOT gate. Truth table of NOT gate. Input 0 0 will get the output 1. Input 0 1 output 0. Input 1 0 output 0. Input 1 1 will get the output 0.
NOR gate. When both the inputs are 0, the output will be 1. When any one input is 1, the output will be 0. Both the inputs are 1, the output still be 0.
0. XOR gate IC7486. The output is high when any one of the inputs is high. The output is low when both the inputs are low and both the inputs are high. Formula for XOR gate. Logic diagram for XOR gate. Here we have the A and B as two input and we'll get one output. Truth table for XOR gate. Input 0 0 output 0. Input 0 1 output 1. Input 1 0 output 1. Input 1 1 0 output. Output will get 0.
XOR gate. When both the inputs are 0, the output will be 0. When any one input is 1, the output will be 1. When both the inputs are 1, the output will be 0.
Half adder and full adder. Half adder. The half adder is a combinational circuit needs two binary inputs and two binary outputs. The input variables designed the urgent and added bits. The output variables produce the sum and carry. The half adder can be implemented with an exclusive OR and an AND gate, and IC7408 or IC7432. Truth table for half adder. Inputs 0 0, sum 0, carry 0. Input 0 1, sum 1, carry 0. Input 1 0, sum 1, carry 0. Input 1 1, sum 0, carry 1. Here is the K map for half adder. Circuit diagram for half adder.
Simulation of half adder. From the truth table, when A is 0, B is 0, the carry will be 0, the sum will be 0. When A is 0, B is 1, the carry will be 0, the sum will be 1. When A is 1, B is 0, the carry will be 0, sum will be 1. When A is 1 and B is 1, the carry will be 1 and the sum will be 0.
A full adder is a combinational circuit that forms the arithmetic sum of input. It consists of 3 inputs and 2 outputs. A full adder is useful to add 3 bits at a time. In full adder, some output will be taken from XOR gate. Carry output will be taken from OR gate. XOR IC7486 or IC7432. Full adder using to half adder. Truth. Truth table for full adder. K map for full adder. Circuit diagram for full adder.
Simulation of full adder. When A, B, C are 0, the carry will be 0 and the sum will be 0. When C is 1, the sum will be 1 and the carry will be 0. When B is 1 and other are 0, the sum will be 1, the carry will be 0. When both B and C are 1, the carry will be 1, the sum will be 0. When A alone is 1, the sum will be 1, the carry will be 0. When A and C are 1, the carry will be 1, the sum will be 0. When both A and B are 1, the sum will be 0, the carry will be 1. When all A, B, C are 1, the carry will be 1, the sum will be 1.
Half subtractor and full subtractor. Half subtractor. The half subtractor is constructed using XOR and AND gate. The half subtractor has two input and two outputs. The outputs are difference and borrow. The difference can be applied using XOR gate. Borrow output can be implemented using an AND gate and an inverter. AND IC7408 XOR IC7486. Truth table for half subtractor. K-map for half subtractor. Circuit diagram for half subtractor.
Simulation for half subtractor. When A is 0 and B is 0, the borrow and difference are 0. When A is 0, B is 1, the borrow is 1, the difference also 1. When A is 1, B is 0, the borrow is 0, the difference is 1. When A is 1 and B is 1, both borrow and difference are 0.
Full subtractor. The full subtractor is a combination of XOR and or NOT gates. In a full subtractor, the logic circuit should have three inputs and two outputs. The two half subtractor put together gives a full subtractor. The first half subtractor will be C and AB. The output will be difference output of full subtractor. The expression AB assembles the borrow output of the half subtractor, and the second term is the inverted difference output of first XOR. Truth table for full subtractor. K-map for full subtractor. Circuit diagram for full subtractor.
Simulation of full subtractor. When A, B and C are 0, the borrow still remains 0 and the difference will also remain unchanged. When C is 1 and AB are 0, the borrow will be 1, the difference will also be 1. When B is 1 and A and C are 0, the borrow will be 1 and the difference will also be 1. When B and C are 1, A is 0, the borrow will be 1 and difference will be 0. When A is 1 and B and C are 0, the borrow will be 0, difference will be 1. When A is 1, B is 0 and C is 1, borrow will be 0, difference will be 0. When A is 1, B is 1, C is 0, the borrow will be 0, difference will be 0. When A is 1, B is 1, C is 1, the borrow will be 1, difference will be 1.
Code converter 1. Binary to gray code converter, gray to binary code converter. Code is a symbolic representation of discrete information. Codes are of different types. Gray code is one of the most important codes. It is non-weighted code which belongs to a class of codes called minimum change codes. In this code, while traversing from one step to another step, only one bit in the code group changes. In case of gray code, two adjacent code numbers differs from each other by only one bit. The idea of it can be cleared from table given below. As this code is not applicable in any types of arithmetical operations, but it has some application in analog to digital converters and in some input-output devices. Binary to gray code conversion. Binary to gray code conversion is a very simple process. There are several steps to do this type of conversion. Steps given below elaborate on the idea on this type of conversion. The MSB of the gray code will be exactly equal to the first bit of the given binary number. Now the second bit of the code will be exclusive OR of the first and second bit of the given binary number. Therefore, if both the bits are same, the result will be 0, and if they are different, the result will be 1. The third bit of gray code will be equal to the exclusive OR of the second and third bit of the given binary number. Thus, the binary to gray code conversion goes on. Truth table of binary to gray code. K-map for G3, K-map for G2. K-map for G1 and K-map for G0. Circuit design of binary to gray code. Binary conversion. Gray code to binary conversion is again very simple and easy process. Following steps can make your idea clear on this type of conversions. The MSB of the binary number will be equal to the MSB of the given gray code. Now, if the second gray bit is 0, the second binary bit will be same as the previous or the first bit. If the gray bit is 1, the second binary bit will alter. If it was 1, it will be 0, and if it was 0, it will be 1. The step is continued for all the bits to do gray code to binary conversion. Truth table for gray code to binary conversion. K-map for B3 and K-map for B2. K-map for B1 and K-map for B0. Circuit design. Code converter 2. BCD to XS3 code converter and XS3 to BCD code converter. BCD to XS3 code converter. As it is clear by the name, a BCD digit can be converted to its corresponding XS3 code by simply adding 3 to it. We can do that either by taking the binary number, add 0011 to it as we did in experiment 2, and get the result, or by converting the binary number to its corresponding decimal number, add 3 to it, then convert it back to the binary. Truth table: BCD to XS3 output. K map to convert BCD to XS3. Circuit design. XS3 to BCD code converter. XS3 code begins with the binary 0011 decimal 3 and it will continue up to binary 1100, where I get the output binary 1001 for input binary 1100. So I need 4 variables as inputs and 4 variables as outputs. With 4 variables I can represent 16 binary values from 0000 to 1111. Since I do not use 0, 1, 2, 13, 14, 15 as inputs, when I simplify the output function, I use those terms as don't care condition. Truth table to convert XS3 to BCD. K map. Circuit design. Design and implementation of multiplexer and demultiplexer. Multiplexer. Multiplexer means transmitting a large number of information units over a smaller number of channels or lines. A digital multiplexer is a combinational circuit that selects binary information from one of many input lines and directs it to a single output line. The selection of a particular input line is controlled by a set of selection lines. Normally, there are 2n input line and n selection line whose bit combination determine which input is selected. Truth table for multiplexer. Circuit diagram for multiplexer. Demultiplexer. The function of demultiplexer is in contrast to multiplexer function. It takes information from one line and distributes it to a given number of output lines. For this reason, the demultiplexer is also known as data distributor. Decoder can also be used as demultiplexer. In the 1:4 demultiplexer circuit, the data input line goes to all of the AND gates. The data select lines enable only one gate at a time, and the data on the data input line will pass through the selected gate to the associated data output line. Truth table for demultiplexer. Circuit diagram for demultiplexer.